madam is available?
Good evening to one and all.
Yes, sir. Yes, madam.
Okay, sir. Please continue, sir.
Okay. Good evening to one and all. On behalf of Department of Electronics and Telecommunication Engineering and the entire organization committee, I, Professor Hemant Mahajan, extended a very warm and heartfelt welcome to today's resource person, Dr. Shika Marwa, to the 5th day session 9 of AICT Atal sponsor 6-day online faculty development program. Welcome, ma'am. Dr. Shika Marwa is the assistant professor in the Department of Computer Science and Engineering at Shiv Nadar University, Chennai. She completed her PhD from the Indian Institute of Technology, that is IIT Mandai, where her research focus on modeling and performance optimization of solar cell, including the Perovskite silicon tandem device. He work involved the investigate degradation mechanism, analyzing electro-optics property, and applying the computational and analytical approach to enhance the efficiency, stability, and overall the performance of photovoltaic system. She is partially interested in advancing device architecture and optimization material properties for the next generation solar technology. Solar technology, Dr. Marwa's research integrated simulation, modeling, and experimental insight to develop the high performance and sustainable photovoltaic devices. She has a published paper in reported international journal and contribution to advancing the interdisciplinary research, bridging material science, electronics, and energy technology. Thank you, madam. I request to madam to start the session. Welcome, ma'am.
Thank you so much, sir. Am I audible?
Yes, ma'am. Yes, sorry.
Thank you so much for the warm welcome, sir. And shall I start sharing the presentation?
Yes, ma'am. Yes, ma'am.
Yeah. Is it visible to everyone?
Yes, madam.
Okay. Hello, good evening, everyone, and thank you very much for, first of all, giving me the opportunity to talk in this FDP, and all the participants who are here to listen to me today. So I have basically I have done my PhD from IIT Mandi, and in my PhD I have worked on silicon solar cells, and then we extended our study to silicon and perovskite multi-junction solar cells. Also, part of my study was working on photovoltaic modules, and to determine how the impact of environmental stressors, they have bad or good impact, whatever the impact is, on the device photovoltaic panels. Another, I also worked on some fabrication techniques. It was an in-house built aerosol assisted chemical preposition technique that was built in there only. And for that we just worked on formation of diodes and formation of different materials on the silicon material. So that was a part of my PhD. So today's topic is from silicon to perovskite photovoltaics: opportunities, limitations, and the road to commercialization. So if I say in terms of silicon, or let's say if I talk about any technology, so the main reason behind going for any technology is because we have to meet the demands of the users. So in the first figure, if we can see, hello.
Ma'am, please, sorry for interrupt. If you
Yeah.
possible, please turn on your camera.
Yeah, sure.
Just we record the some snaps.
Sure. Just a second. Yeah, is it fine, sir?
Yes, ma'am, but you are not visible.
Oh, wait. I've turned on my camera actually.
Yes, sir. Madam is visible.
Okay.
So shall I continue, sir?
Yeah, yes, ma'am.
Okay. So, if I say basically, if I talk about why do we need any technology and why do we need to move towards the other technology, it's just because of demands. So, we have this international energy outlook that shows us certain graphs and they show us the history and the projection. So, in the first graph, if we see our electricity that is used in the previous years, that was mostly through the fossil fuels that we were using in terms of the trillion kilowatt hours. But we can see that since COVID, I would say there has been changes in the rules and regulations. So, near about 2018 to 2019, we can see that the contribution of other renewable energy resources has been increased. And if we see the projection till 2050, uh, there are many renewable resources available right now. We have hydro, we have wind, we have solar, we have so on and so forth. So here if I say we have, it's projected and it is being seen that the solar is has been emerged and it is going to emerge as one of the very prominent energy resource in the coming years. The reason is obviously because it's been, I would say it's been like 70 to 80 years since we have started working on solar, since its past like if I say in terms of its first solar cell when it was discovered. And then right now we have for silicon, if I say, we have reached its Shockley quasar limit. So yes, solar has a scope, provided what type of technology are we talking about. And if I say in terms of the second figure, that corresponds to basically the contribution or the use by the other countries. So yes, rest of the world has been using this technology, but again, its projection till 2020, 2050, if we see, the major consumption is being done by China. Obviously, there are certain policy frameworks there in China, and the, I would say, the installations and the fabrication that is happening over there. So there are many factors that leads to the increased solar generation in or any type of generation in a country. But if we see from the here like corresponding to other, even from the US, Middle East, if we see, the contribution of solar in India is also going to rise. And that is one of the reasons that we are going towards now make in India, and we are going towards renewable resources in the coming years. So this is one of the reasons that we are going towards technology. And again, the reason behind this is that we have almost at the verge of fully exploiting our fossil fuels that are present. And obviously, when we are using these fossil fuels, they have a detrimental impact on our environment too, which leads to the air pollution, ozone layer depletion. And moreover, if I talk about electricity demand, so that's why a projection shows that it is going to increase every year by 20 to 1 not if I say. So we need to have a projection of near about 52 terawatt, and that's quite huge. And it's difficult that we have when we have finite resources. So making use of those resources and to attain that this much limit of energy and without hampering the environment, this is actually next to impossible. So that's why we need to have certain clean, reliable, and decentralized energy resources. And solar PV, by PV I means photovoltaic. So solar PV has been emerged, and it will be a very prominent solution for our future energy needs. So this is a very prominent chart if anybody is working in solar cell area. So this is basically a best research cell efficiencies, and it is provided by NREL, that is National Renewable Energy Laboratory. And again, its name is nowadays changed to something else. So this is the chart that has been providing, and it gives us the idea about how different solar cell technologies, since the day it was revolutionized and till today, what efficiencies they have achieved in the coming years, and what is their from which companies they are being achieved. So that has been showed in the NREL. So this basically is the best solar cell efficiencies. So here if I say in terms of silicon, so here first of all I'll start with the silicon, because silicon is something that is acquiring 95% of our PV market. Mostly it's crystalline silicon solar cells. 95% of all the PV modules that we have right now, they are made up of silicon. There are certain reasons behind it. First is stability, because it's not going to degrade so early. And yes, there are also limitations that I'll be discussing. But yes, for 15 to 20 years, if I talk in terms of reliability, a material should be able to sustain at least 15 to 20 years. That's why we see the PV panels getting installed at a commercial level, even at our residential level. So why so? Because 15 to 20 years, that's a huge thing, right? Our cost of installation is recovered in few years, maybe 2 to 3 years or 4 years, let's say 5 years also. But still, down the line, if I say 15 to 20 years, that's again a profit. And through grid lines, we can transfer that an extra energy that is generated, and we can give it to the government also, so we can get paid also. So there are different policies for that. So NREL is basically showing, if I say this particular graph, if you can see this, for silicon, we can see it has almost silicon has almost reached its SQ Shockley acquisite limit near about 27.8%. For different technologies of silicon, we have HIT, silicon heterostructures, thin film clusters, multi-crystalline. So they have almost reached some limits. Then we have certain thin film technologies, and then we also have emerging PV. So emerging PV is quite interesting. That is, we have emerging PV. The most commonly that we use is the perovskite. So here, if you see emerging PV, and by emerging PV here I mean the single junction. Previously that I talked about, silicon was a single junction, one technology at a time. So similarly here also, if I say perovskite, one technology at a time. So they are, we can see that the limit that they are reaching in few decades, because it started since it's just been a decade since we have come up and started exploring the perovskite solar cells. And in that much amount of time, we can see its efficiency has been reached, and it is nearby competing the silicon solar cells. So does it have a potential? Yes, it has. So similarly, if I say perovskite tandem cells, by tandem I mean multi-junction solar cells. So yes, tandem is also reaching near about 30.1%. So that is also attainable if I say two technologies together, and I'll be discussing that in the coming PPTs. Then we have hybrid tandems. By hybrid, I mean one is perovskite tandem means we are using perovskite, and by hybrid, I mean we are using two technologies at a time. So right now, one of the most commonly used technology under study, I would say, is the perovskite silicon. And perovskite silicon is something that is quite interesting, and it is, has taken the interest of many researchers. The reason thing is that again I'll be discussing what is the reason, because it is complementing the silicon industry. So this is just to give an overview what is the current status of all the technologies right now. Then just the evolution of photovoltaic technologies that I have shared. So there are different generations quoted by different researchers. So we have first generation, second generation, third generation, and fourth generation. So in the first generation, we talk about the initial cells that we started with, the conventional silicon solar cells. Then second generation is the thin film solar cells. Here also comes the one that we are using right now. And third generation is organic cells, the dye-sensed DSSC, perovskite and quantum dot solar cells. And the fourth is hybrid solar cells, or we can call it as a multi-junction solar cells. So these are the evolution of photovoltaic technology so far. This figure, if you see, just now I said that silicon has reached its limit. So by limit, I mean that silicon is a material, it's a semiconductor material. So every material has certain properties, and we cannot exploit its uses fully. The reason is the band gap, right? So here, if you see the first graph, that here we have a certain AM 1.5G spectrum that is reaching my device for a certain wavelength. But here we can see that from 300 to near about 1100 only, or 300 to so only this much. If I say the contribution or the power of sunlight that is getting converted to electricity, and that is being converted into a powerful source of energy is very less, because gray is the area that is what we are getting from the sun, and red is something that we are converting it. So we can see that most of the light, like I would say 50%, that is not being used. More than 50% is not being used. So we are able to convert only a few portion of the sunlight to our usage, or to convert it into electricity. The reason is, again, there are certain losses happening in the material, thermalization losses. There are certain recombinations happening in the material. So that I'm not covering right now, but you can refer to any paper, and then you can see what are the reasons why solar silicon is not enough. Yes, there are advantages of silicon that I have discussed, that it is not going to degrade. You can expose it to the environment, because every material, see, if I talk about sunlight, sunlight is, we have to keep the material PV panels, if we have to keep it outside. So if it is outside, it has to undergo various environmental factors. It has to undergo different ranges of temperature. It has to undergo moisture, then light exposure, then different ranges of lights that is falling on it, right? So if a material can sustain all the environmental stressors and then again retain its properties to a certain limit, and that is for certain range of time, then we can say it is reliable. So yes, silicon is reliable. But as I have said, the limit is not more than 30%. Let's say if 100% of light is getting is reaching our Earth's surface and then it's not getting converted fully, then we need to think of some alternatives. So for that, what we do is we make use of this particular silicon technology, and what we do is we integrate it with some other technologies. So here if you see, this is just to show a two terminal tandem efficiency as a function of cell band gap. So here if you see that generally what we use is silicon is our one of the bottom cell, and then we use a top cell on the top of it so that we can extract the maximum efficiency of our sunlight. So here if we see 1.1, if the because the band gap of silicon is 1.12, so we have a graph here to correspond to 1.1, and to attain the maximum efficiency, the one that is in purple shade, we can see that we need to have a band gap that is more than near about 1.6. So the band gap should range from 1.6 to near about 1.75, right? Again, if we go beyond that, again there will be losses, and the efficiency of a material decreases. So this is something that we need to integrate two technologies together. So there is a limit to everything. So if I explain this in terms of a proper device structure, so I have this schematic of silicon perovskite tandem solar cell that I was discussing. So here we have a silicon bottom cell that is shown here in maroon color, the purple color, the red color or maroon color. Then in between, I have a junction layer that has to pass the certain charge carriers through each other. Then I have the perovskite top cell, and then on the top of it, I have a transparent electrode through which my sunlight should reach the device. So here, when my sunlight reaches, what happens is when the sunlight reaches the transparent electrode, the top cell, the perovskite solar cell, it could be any cell, but mostly we make use of perovskite. We'll discuss the reasons. So this top cell absorbs the high energy photons. So whatever is the high energy photons or lower wavelength, I would say, high energy photons, they are absorbed by this perovskite layer, and the other part, the low energy photons, are absorbed by the silicon bottom cell. So here, instead of one technology getting constrained to a certain wavelength, we have two technologies in which we can make use of the whole wavelength. So here the tunnel junction that we have, this thin tunnel junction, it is basically used to connect the both the top and the bottom cells. So if you see this graph, the B figure here, so here it's just corresponding to what I showed you earlier in terms of the silicon. So here if we see that the black shaded line is basically the solar irradiance that is falling on our device, and here if we see when the sunlight reaches, what happens is the top cell, the high energy photons, or the high energy photons, basically they are absorbed by the perovskite. So this, for this particular range from 300 to 800 near about, it is absorbed by this perovskite, and rest of the range is absorbed basically by the silicon. So instead of getting a portion of the AM 1.5G spectrum, we can have a full range of spectrum, or at least certain range that is more than the silicon capability to make use of the AM 1.5G spectrum. So this is something very interesting, and I would say that silicon, why I'm integrating silicon with the perovskite, because perovskite has certain properties. As just in the previous slide that I discussed, we need to have a band gap range corresponding to silicon. So perovskite has certain properties. It can tune the band gap. So I'll be discussing those properties with you. So again, what is the need for the perovskite solar cells? Because silicon is not enough in the coming years. So we have a huge global demand for sustainable and renewable energy, and obviously to mitigate any environmental issues. Another thing is it's lightweight and flexible. So if it is lightweight and flexible, we can also use it in BIPV. So you might have heard the term BIPV. building integrated photovoltaics. So there also it can be used. And raw materials that is being used in perovskite solar cells. So the raw materials are not that expensive; they are quite cheap, and the cost of fabrication is not are also not expensive if I compare it with in terms of silicon. And if I say in terms of the mass production, then the cost of production is quite less. So yes, perovskites can be considered. Again, they can be scalable. They, because there is a need for scalability, they can be scalable, addressing certain issues that we will be discussing. And if they're scalable, they should be affordable, and they should also provide us the efficient solar solution, so that we can have a transition towards the clean energy in the coming years. So just to quote certain differences between the perovskite and the silicon. So silicon, as I have already said, that commercially available efficiency for crystalline silicon, or the silicon that we are using right now, is 20 to 22%. Because experimentally, although we can achieve 27, 28%, but when it comes to getting this efficiency at commercial level, that's this total efficiency is near about 20 to 22%. And even if we are able to retain 90% of this efficiency for a period of 15-20 years, that's actually a good thing. In case of perovskite, we are not having anything in terms of commercial level. We are still at the laboratory settings, and we can obtain an efficiency of 26%, near about. Silicon, if I say, that's a very matured manufacturing technology, because most of the world, as I've already said, 95% of the market of photovoltaics is dominated by silicon. So because if it is dominated, obviously its cost is also a factor here. So here we can see, if I say in terms of worldwide, so in terms of US and other places, so it per watt it would cost about 0.4 to 0.5 dollars. Whereas if I say in terms of perovskite, the cost quite could be decreased. The reason is, again, I have said that depending upon which method of fabrication we are using. If anyone of you have worked on silicon, you might be knowing that the material is not a problem, but the actual cost through which it is getting manufactured, that is very expensive. So and moreover, the temperature processing, uh, like at which temperature the processing is done, that is also something determining whether there will be any defects in the material. And also that is also something determining the cost, how many pieces are actually able to retain and actually able to have a final check once it is fabricated. But in case of perovskite, if I say, they require low temperature processing. Silicon, they are quite rigid and heavy, and they are not flexible. But in case of perovskite, there is a possibility, and the work is being done, and they can have a flexible substrates which will enable versatile applications. Silicon, if I say, they are well established for mass production, and they have shown scalability, but perovskite is still yet to be get scalable, so that is still at a very early age. Toxicity, so this is very important factor that again I'll be discussing in the coming ppts. Toxicity is something we have to address, because in perovskite we make use of certain layers, especially lead is there in the perovskite precursor material, so that is having a detrimental impact on our environment. Whereas in case of, if I say, silicon, we do not have any such layer that would increase the toxicity. So yes, their toxicity is always there when you're working on chemicals, but again the level of toxicity is quite less in terms of silicon. But in perovskite, there are chances that due to the increased lead content, it will have some detrimental impact on our environment. So just to give you a brief idea, what is a perovskite? So it is just a EBX3 structure. And by A, I mean any monovalent cation. It could be methyl ammonium, formamidinium, cesium, rubidium, any type of a material could be there. And B is again a divalent metal cation. It could be lead, it could be tin, it could be bismuth. There are many materials just to replace the lead that are there in the market. So that can be anything. And X is basically, I have not mentioned here. So X is basically any halide. Chlorine, oh yeah, it is mentioned here. So X is halogen, anion, it could be chlorine, bromine, or iodine. Okay. So, so those who are new to this, let me tell you that silicon is just a silicon. So it has a fixed band gap. But in case of your perovskite, we can vary A A could be either of the material, or it could be combination of any of the cations that I've shared. It could be either methyl ammonium, formidinium, or cesium, or it can be a combination of methyl ammonium plus formidinium, formidinium plus cesium, or all the three combined. So that is very much possible. Similarly, if I say in terms of B metal cation, here also we can have a combination of either lead or tin, or a combination of lead plus tin. Any material can be used. And for halide also, any combination of all the three halides is possible. Now, why are we doing this? We are doing this to attain a band gap that is that should give us a higher power conversion efficiency, right? So depending upon a different substoichiometric coefficients, depending upon different fabrication methods, we can have different band gaps. So I have a different a separate ppt for that. I will show you how it varies. So a very first material of perovskite, and this was calcium tin tri oxygen, so calcium tin uh, 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 so this was used to first as one of the perovskite material that was used at a very initial stage. But now we have moved from this particular material oxide, sorry, calcium titanium oxide trioxide. So from this particular material we have moved to different materials of perovskite, depending upon our requirement, or depending upon what our structure is. So, what are the perspectives of perovskite? Perovskite have its own advantages and it has own disadvantages. So, first is they are perfect partners for the matured silicon technology. So, this is very important because let's say if I make only perovskite multi-junction solar cell. So, what happens is I have to work on one technology and my system is dependent only upon one technology. I have to start the whole world will have to work on it, or I need to have a different lab setup in which only perovskite materials can be manufactured. But if I say I have perovskite silicon, then already in the world we have silicon labs established. We have commercialization of silicon very much there. Now, can those labs also include some portion that is required for the fabrication of perovskite? So we can integrate one mature technology with the new technology, so that becomes easier. So that is why it is just like one of the paper is there, that the marriage between the two technologies. So yes, it's a perfect they can be perfect partners. Another thing is band gap tuning. So, as I have said, that depending upon their different stoichiometric, substoichiometric coefficients, depending upon their different layers, we can tune the band gap. Highly efficient, as I've already said, in the last decade only, we have obtained a very good efficiency. So yes, they are quite efficient. High absorption coefficient. So their absorption coefficient is also quite high. They have a very good high diffusion length and high open circuit voltage. Another thing is they have low processing temperature. Okay, so this is very important because in silicon we have certain if anybody has worked on carrier selective contact architecture or hetero intrinsic structures, HITs for silicon. So we see that for that there are certain layers in which the temperature should not increase beyond 500 degrees Celsius, because then that layer starts to degrade. So we need to have a technology on the top of silicon that do not hamper its properties, but it just adds a value to it. So perovskite, it can be manufactured, like if we have a processing temperature of near about 200 degrees Celsius, so it should work. So yes, this is one of the advantage of it. Disadvantages. So this is a very crucial thing that needs to be addressed. First is stability issues. Uh, Stability issues, if I say, so most of the research for this perovskite solar cells are being done in the glove box, and there are different methods of deposition of the perovskite layers on a device, for a device. So what happens is, as long as it is there in the glove box, it's not a problem, although it degrades there also. But the moment it comes under a contact of external environmental factors, be it light, be it temperature or moisture, it degrades, it loses its property. So stability is an issue because certain perovskite materials might not even sustain 1 hour, and certain, so that's why I have said that we are working on, the research is going on, because the possibility is always there. Yes, this is going to be getting mature, and then it has a potential to be used for the commercial applications. But Right now, if I say yes, people are working on different A, B, and X components, so that we can have certain, the radiuses should match, certain ionic bonding should be there so that they do not degrade. So I'll be discussing some of the compositions that are there in the market and how it is getting used and what are their potential applications. So that is something that needs to be addressed to address the stability, because most commonly used material, if I say, that is this methyl ammonium lead iodide. So this is the most commonly used material. It has been researched a lot. A lot of work has been done in this with this particular material. But if I say in terms of stability, this material is not good. In terms of toxicity, yes, it will increase the toxicity, because as I have said, the lead is there, PBI3. So lead is also there. So that is also going to increase the toxicity of the material. So this is also something that needs to be addressed before using it for the commercial applications. So a simple perovskite solar cell structure, if we see what is the architecture of it. So basically, first of all, any solar cell need to have, first of all, the active layer or the absorber layer. So it will contain one perovskite active layer, then transport layers, electron transport layers, and hole transport layers. Then they need to have a transparent front electrode, TCO, metal back electrode, and then also materials generally doesn't work directly, because if I say in terms of device engineering, or when we go for interface engineering, we need to have some interface layers also to prevent any recombination between the materials. So here, if I say, there are two structures of perovskites, or two configurations that are being used. So first is a standard or a normal configuration in the form of NIP. So here, if we say, towards the transparent electrode, we have ETL, then we have perovskite, then we have HTL and metallic anode. And in case of inverted structure, first of all, we have a transparent electrode, then we have HTL, perovskite, ETL, and then cathode. So we have two types of structures in between also, because see what happens is, if the in absorber, when the light falls on the absorber, there is a movement of the charge carriers. Okay, so there will be electrons and hole, there will be electron hole pairs that are getting generated. So we need to transfer these electrons towards the ETL and holes towards the HTL. But what happens is, at the interfaces also there are recombinations happening, and we need to prevent that, so that at the end, at the wires that we can see, we can have hole and electrons. So to prevent any such recombinations, we have certain interface engineering being done in both the cases. So we have different type of interface layers. Anybody who is interested in it can explore some papers, or we can have a discussion related to this. Then a working principle of perovskite solar cell, be it any solar cell, we have the same working principle generally. So light absorption is being done with the help of a perovskite absorber layer, in which the excitons are generated. Basically, these are the electron and hole pairs. And then these electrons, excitons that are getting generated, they need to be dissociated to form free electrons and holes. And once they are free to get transported, we need to have the layers, that is electron transport layer and hole transport layers. Now the question should be how to select what is hole transport layer and what is electron transport layer. That is, again, we have to study basis on the basis of their band caps and how the bands are aligning to each other. I'm not shown here, but then again we have to see how the band, how the valence band, how the conduction bands are, so that electrons can flow towards the electron transport layer and holes can transport towards the hole transport layer. That is one thing. Another is charge collection. So we have electrodes at both the ends, at the electron transport layer and towards the hole transport layer, where we need to collect it. Okay, because once they have, from the transport layers, they need to reach the wires or to the electrodes, because if they are not collected, there are, again, there is a possibility of recombinations. So in order to have minimal recombination, we take those electrodes there, and at the end we can have a once they are collected at the electrodes, so at the power output we get the collected charge carriers that we receive at the output. They basically generate an electrical current powering external circuits. So we can connect any external circuits with the help of that power. Now again, the question is how much power is getting generated. that will be again, that is again a separate topic here, in which we talk about implied open circuit voltage, what is the open circuit voltage getting generated corresponding to its band gap. All those things needs to be taken care of, because if I say photovoltaic module and if I say photovoltaic panel, they are combination of different photovoltaic cells. So how much one is generating, and then it needs to be multiplied with different cells connected together. So we have to take care of that. Now, what are the fabrication techniques of perovskite solar cells? So, or the method to make one perovskite solar cell? So, first of all, what we do is we prepare a precursors. Perovskite precursors needs to be prepared with precise stoichiometry to ensure optimal material quality. This is very important, that we need to select those material combinations for which we want to make a perovskite. As I have said, any combination for any cation or anion that you want to take, we need to have a proper stoichiometric calculations done to prepare the precursor. Then those precursor is applied on thin film using spin coating, spray coating, or vapor deposition. Now we also have a co-evaporation technique. So there are multiple techniques available in the market, so we can use any of those techniques. Slot die coating is also there. So there are multiple techniques in the market. Any of the method can be used for that, but most prominent that I have seen is spin coating. Most of the labs have that spin coater with them, so we can apply a thin layer using the spin coater. Then we have to integrate it with the help of charge transport layer. So once we have applied the thin film precursor, perovskite precursor, then on both the sides we need to also integrate it with charge transport layers. Once the charge transport layers are done, then we need to also fabricate electrodes on it, electrodes and substrates into a functional device structure, so that we can have a proper working functional device. Then, as I have said, that there are chances that this device can undergo an environmental stresses, and then it can undergo, I would say, degradation. So to prevent that, the most important thing that is done is encapsulation. So it is basically, encapsulation is we seal these devices with the protective layers, so that our system is not getting prone to the moisture or UV exposure or any light exposure that we are getting from our environmental stressors. So we prevent that. Then if I talk about commercial scale, then we need to go for another. Roll to roll printing is there, large area coating is also there if we want to go for commercial scale manufacturing. So this is still under study. One of the paper that one of the research I was seeing, that it was at Oxford PV, I think. So they have certain a very production line for this perovskite, and that is very, again, at a very initial stage. So they are checking whether the potential of perovskite solar cells is there or not. So that is one of the production line I was seeing. Another I was seeing some Swift Solar is also there. So they are also working into that. They have actually partnership with certain commercial companies, and then checking the commercial feasibility of these materials. So yes, we have a distance to travel, but yes, research is going on in this field. So, growth and development of perovskite solar cells. So, as I've said, that in 2012 only, the initial power conversion efficiency was obtained for the perovskite solar cell. That was about 3%. So, the efficiency at that time, the efficiency was quite low, and again, the stability was again a problem. So, then by 2020, the research was basically on increasing efficiency, and also on working on the stability with corresponding to the environmental stresses such as moisture, heat, and UV exposure. Then again, 2021, some work has been also been started for commercial viability. As I have already said, roll-to-roll printing and all those methods are being seen. But 2022, the efficiency was reached near about 25%, and obviously the degradation mechanism happening in the material, the device engineering, that has also been increased in that 1 decade period. So that was also properly understood. After that, very interesting thing has been seen, that based on those data that has been gathered in a decade. So researcher and the scientific community, what they have started is they have started analyzing the trends, and they have started to make predictions based on the previous done data, because in one decade the rise of this particular material has been too much, like it has increased a lot. So instead of going, because again fabrication and stability is an issue that needs to be addressed. So what people have started doing is that based on those researches, if we can make any predictions for the future, and then we can work on the efficiency and stability, and also on the cost reductions. So that is something, again, if you have seen some papers on machine learning, so we can see that that has also been at the search. Again, advancement in large scale production and tandem cell integration, that is also being taken care of. Not only the individual perovskite solar cells, but also multi-junction perovskite solar cells are also the use of those materials, and then to understand their physics, to understand how they work, to understand the degradation mechanism, that is also being increasing. At a very minute level, they have started studying it. So yes, this is quite interesting. So commercialization, if I say again, not, we have not reached that, because again 12 to 31% has been reported, and but yes, they have a huge potential to replace the current technologies. They have the potential to replace, or I would say they can integrate with the existing technology. So with the silicon PV technology also, it can be integrated very well. So as we have seen from our understanding. So the challenges that I have said, that the degradation is a challenge, stability is a challenge, toxicity to humans. They are going to increase the pollution to ecosystem, the cost, the upscaling. So all those things are a challenge, and certain measurements and certain precautions needs to be taken care of. So first of all, we will study the just the issues that they have at a very basic level. What is different instability and degradation issues in a perovskite materials that has been seen so far. So first is the thermal instability. So by this I mean that generally before you're taking any material into account for commercialization, they undergo certain tests. So one of the tests that we take care of is 85% 85% relative humidity and 85 degrees Celsius temperature. We expose the material to that much environmental stress, and then see how it behaves. So if I say in terms of the thermal instability, so this particular material, mostly the studies, as I've already said, that most of the studies has been done on, a lot of studies has been done on methyl ammonium leadite. So just to give you an idea of it, so when they are exposed to near about 85 degrees Celsius, what happens is this uh, methyl ammonium iodide and methyl ammonium and NH3 ammonia. So what happens is these gases, basically they are volatile and they try to evaporate. And what happens is when they are exposed to such temperatures, they leave a residue which is lead iodide. So this lead iodide is again something, again it has lead, and this residue that is left behind, this is of no use, because this process is irreversible. We cannot reverse this because it is volatile. And why this is happening? Because the formation energy of this methyl ammonium leadide, it's quite unstable. So again, I said that when we are working at the device level, we also have to come back to its to understand how its chemistry works, how the material works, and how the energies work in this case. So if the formation energy is quite less, so this makes this material quite unstable, and which leads to the decomposition and releases these gases. And another thing that has been seen is if I talk ZNO, that is zinc oxide and methyl ammonium lead iodide interface. So because any material, any absorber layer has to be integrated with the electron transport layer and hole transport layer. So we have seen that when we are integrating this material, when we are using zinc oxide as one of the transport layer, and then at the interface, what we see is there is a degradation happening due to annealing. So when we are increasing the temperature, there is a degradation. So because of that, what happens is, again, this the particular material, the particular this MAPPI3 that we have, the absorber layer that we have, that again decomposes to these residues that I have said earlier. So this is something that is increasing the instability of a material. So these things needs to be taken care of. Another is humidity exposure instability. Okay, so here also when we expose certain, as I've said, humidity is near about 85-degree temperature is the thermal temperature that we talk about, and humidity, when we expose this material to near about 85% relative humidity, so what happens is there are certain again issues reported, and that also again degrades our particular methyl ammonium lead iodide. What happens is if we have a limited amount of moisture, so that can sometimes improve the crystallinity, that can also improve the device performance. But if that humidity, that particular level of the humidity, that goes on increasing, so what happens is this excess humidity degrades as methyl ammonium ion absorbs water. So what happens is now this water molecules starts to interact with this methyl ammonium ion, and then it disrupts its lattice, the internal structure of the methyl ammonium lead iodide. So what happens is this material actually when the water and oxygen are getting reacted, so what happens is under this the whole system it starts degrading, and it forms these solids and the gases that I've shared here. So again it will form hydrogen iodide, it will form methane as one of my gases, and these solids residues are left behind. And water triggers decomposition even without light. So even if there is no light, then also the decomposition increases. So not only I would say not only in the presence of light, but in the absence of light also it is acting as one of the decomposition factor impacting the device performance. So that is again and again lead iodide is one of the residue that is getting formed here, and which is not good for the environment. So again we have to think of some alternatives for this particular material set and for this particular technology. Another is we have light oxygen exposure instability. So when they are exposed to certain light, because as I have said that once they are exposed to light, then also the degradation happens. So what happens is when we have light and then excess of light is there, so what happens is there is a formation of superoxides. So because of that, what happens is this methyl ammonium lead iodide, it is broken into lead iodide, and it is also broken to iodide gas. So and again in the previous case we have seen that if there is moisture but there is no light, then also there is degradation. But here even if there is light and there is no moisture, then also there is a degradation. And but here again as a bioproduct we have one of your lead iodide as residues, and if I say in terms of residues, they are lying on the material surface itself. So if there is a little bit of residue, that's not a problem, but over time if this residue is increasing, then it will have some impact on our device performance. So this is something that needs to be taken care of. Next is mechanical damage. Okay, so mechanical damage. So most of you know that we are just working on a glass substrate when we work on perovskite solar cells. So what happens is, even if there is a crack or a strain, that degrades our device performance. Although it is there in the silicon also, silicon is quite brittle. That will also degrade our performance. So same is the case here also. They are prone to a mechanical damage in which a crack or a strain, they can reduce the efficiency of our perovskite. They are brittle, but they have high mobility, enable self-healing. So we'll be discussing some self-healing materials, how they can, if there is any mechanical damage or any kind of damage happening in the material, with the use of certain polymers, how they can heal themselves. That is also something we will study. So if I say in terms of perovskite, in terms of durability and portable materials, so if we have perovskites, flexible perovskites, then yes, we can make use of certain self-healing materials in which we can increase the durability of our material. So I'll be just sharing that with you shortly. So these are some self-healing perovskite solar cells and their mechanisms. So what happens is, this is again not much work is being done here, but some of the work has been reported, so I was just going through that. So what happens is, as I have said that there are certain the impact of environment is always there. So what happens is, if we say if we have a moisture if the external trigger is only moisture, so what happens is when we are making a precursor in the perovskite, for example, I've said methyl ammonium lead iodide. So if I'm making that particular precursor, in that what I can do, I can make use of one of the polymer inside it, let's say PEG, polyethylene glycol. So what happens here is, if I make use of those polymers while making the precursors, I can increase the lifetime of my material, or I can increase the efficiency of a particular material, or I can prevent this degradation. So here, if you can see, the first figure is when we are using PEG as a in our precursor. So here, if you see, even after 45 seconds, after certain time, first of all, what happens is there is some degradation, but with time it self heals itself, and then the whole the in the first A, when we had PEG, the first and the last figures are almost the same, so they are retaining its phase. Because phase, we can see with the help of our naked eyes, there will be change in the color. So yellow color is just basically showing that the phase has been changed. But initially, yes, there was some certain phase change, but then it has self healed itself. So what happened was that when we used PEG with the methyl ammonium lead iodide, it basically formed a compound, lead iodide and MEI plus MEI water. So what happened is, in the presence of this polymer, what happened after certain time, so methyl ammonium and the latter methyl ammonium and H2O was formed, and lead iodide was formed. But within some time, what happened was the H2O got evaporated, and then it retained its MEI, and then again we got MAPBI3. So its film was restored, and power conversion efficiency was also restored after a certain amount of time. Then we have another PVP, polyvinyl paralodin material, in which again we see that, if we see the first figure, in which we have not used this material, and then we can see that it is repairing itself after certain amount of time. So we can see that if there is MAPBI3 alone, yes, it is getting repaired after certain time. But if we are making use of PVP, we can see the process. We can see that this material is almost, the first figure and the last figures are almost the same. It means that it has retained its phase. Why? Because this PVP, when it was used with the perovskite, it basically formed a barrier. It formed a barrier against the moisture or against the H2O. So what happened is, it formed, and it, the H bonding that it formed, it actually slowed down the crystallization of methyl ammonium, and it also reduced its trap state. So thus what happened was that stability against the moisture and the humidity has been increased. Similarly, if I say copolymer TiO2 ETL, so instead of using a normal titanium oxide electron transport layer, if we make use of copolymer titanium oxide layer, so in that case, what happens is, the hydroxyl groups of water, because we are exposing it towards the water, so the water, what happens is, it facilitates MAPBI3 regeneration. The water, with the use of this particular copolymer, what happens is, the hydroxyl group bond to the N atom of NH3 plus and lead iodide, or PbX2, whatever material we have here. It forms a bond with this, and with time, what happens is, the water evaporates. So it is basically a self-healing, instantly and fast recovery. Another we have is the ITO electrode. So ITO electrode is generally, instead of using any other electrode, if we make use of ITO electrode, again, electrodes are necessary if we want to have the charge collected at the final end. So what happens is, if there is any ion accumulation happened when we are using ITO and when we are using perovskite interface, so what happens is, in the dark, because of this ion accumulation, so this ion accumulation starts to fill the vacancies in the dark. So if there had been any vacancies, because of this ion accumulation happening, because of the moisture, they start to fill the vacancies that has been there in the dark. So it prevents the degradation. So we can see that if we have a normal silver coated material, we can see that there has been the power conversion efficiency, the normalized power conversion efficiency, that is decreasing. But if we have ITO as one of my electrodes, we can see that it is still a constant. So yes, it is one of the material or self-healing material that can be used. Challenges. So again, another minimizing the challenges. So if I say in terms of lead-free materials, so one of the material that we can use is the tin, and we can use germanium, and we can use bismuth. Okay, so how we can replace any material, although it is lead is increasing the toxicity, but then also it is one of the material that is also increasing the stability also. So You can read few papers in which if there is no lead, the stability is an issue, but if we are increasing the concentration, that is increasing the toxicity. So what we can do is, can we have certain materials from our the list of available materials that can have the same properties as lead, and they should not hamper, or they should not create any problem to our ecosystem. So yes, there are certain materials most commonly used and that is being explored nowadays, the tin. So their electron configuration is more or less the same, and their ionic radius is also suitable, so they actually fit with this they should actually fit with the cations that we have, methyl ammonium and formamidinium, and then we have cesium, all those materials that we have. So we need to have certain materials that should fit with that. So yes, this is one of the material that can be used. But again, to this material also, for the tin also, there are certain issues. First is they are highly conductive, but they have poor reproducibility. That is one of the thing. Another is they are quite unstable. For lead, I just said that lead is quite stable, but for tin it's quite unstable, because it basically from tin it gets converted to Sn2 positive, so it becomes an ion, and it leads to oxidation and rapid crystallization. So that is something that is not acceptable. Still work is going on. And they have a quite rough morphology, they have high defect in density, so because of that the efficiency is quite low. Although with lead there is toxicity, but stability and efficiency can be improved if I do hit and trials with ABX3 materials. Okay, sorry, A and X materials, because if I fix B as my lead, but if I use tin as my material, then it is less toxic to the environment, but then we have to compromise with the stability and the efficiency. Then improvements can be done when we make use of PCBM based devices, superior with the stability without encapsulation. We have another set of materials available in the market, which can work on stability, which can work on efficiency, all those things. So, or another thing that can be used is we can make use of a combination of lead and tin. So if not, we can, I would say, exploit the stability properties of lead, and then we can also exploit the I would say the less toxicity properties of tin. So that is also being explored nowadays. So we have mixed lead and tin halide perovskites too in the market. So that is also something that can be done. If I say in terms of self-healing perovskites, if I say in terms of mechanical self-healing, if there is any problem, because here we have some flexible perovskites. Here also we have similar polymers, as I've discussed when discussing the exposure to the moisture. So here also, when they are triggered with heat and there is any mechanism or any bending happening in the material, or there is any crack, so what happens is, if I use this particular material, PU, polyurethane, if I use this, so then it can combine with my particular perovskite that I'm using, and then it will see that after some time it will start to self heal itself. Now, by self heal, I mean that it will start increasing, it will repair itself. By repairing its cracks, it will heal its defects, it will passivate its grain boundaries, and also maybe with duration of time, let's say the power conversion efficiency has been decreased, but after certain time it will retain its 90 to 91% of its initial value of power conversion efficiency. So yes, this can be used. Another is TUEG3, thiourea triethylene glycol. So it triggers basically at the room temperature. Here also it is also acting as a self-healing material, in which there is a possibility that they can correspond to a proper mechanical strength, and they can also retain good electronic properties, again the power conversion and the efficiency of the perovskite material in a better way. Next is their PVA material. Again, its trigger is moisture, and it also has the capability to repair any cracks, to heal itself. And some of the works has been reported with formidinium lead iodide. Formidinium lead iodide. So these works have shown that yes, this is very much possible to include self-healing polymers with any of the perovskites, and then we can at least reach somewhere in terms of the stability and in terms of making minimum issues with the long-term stability of a material. So this can be done. The material cost. So here, if I say in terms of the material cost, for the perovskite solar cells, if I say yes, in the coming years, in terms of the government spending funds, in terms of companies showing in the interest in the coming years, we can see that by 2050 we can see that it is going to give an employment also near about 11.5 millions employment is also going to generate. Investment is also going to be there by 165 billion US dollars, and then the levelized cost of electricity, that is also going to decrease in the coming years. So yes, it has a scope, and because it is a low cost material, so obviously it has a potential if it is used at a commercial level. But considering that all the issues that we have said, are those issues addressed or not? If those issues are addressed, then we can make use of it. And a major cost reduction driven by cell efficiency improvement and system level optimization. We also have to work on its optimization also, and efficiency also, because if I say cost is determined by many factors, so all those things has to be taken care of. Okay. And yes, it has a possibility, if it is done at a large scale, it has a possibility with proper investments, it is very much possible to have job creation in the solar sector in the coming years, although it has created many, because every now and then we can see some companies popping up, but yes, it has a future in the coming years. Scalability is again one of the things that I have said, that the toxicity is the problem with lead-based perovskite. So one of the solution is developed lead-free perovskite, and I have said that Oxford PV and Swift Solar are already working on it. Manufacturing consistency, we need to work on its quality control, process optimization, because uh, the method in which it is being made, that is also something determining the cost of a particular device structure. So corresponding to whatever the fabrication material processes that we have, if we can come up with one commercial method that could be used by everyone, and we can have standards set for that, so that will also be something that we can have a particular consistency. Because right now we are working at a very minute level, we are working independently, we are working at the lab level, but certain standards, for example for silicon we have set some certain standards, for perovskite also we need to set some standards, and then we can work on its optimization, we can work on its quality control. And again, Soliance is one of the things that is working, and it is a collaborative R&D working with solar, Oxford PV also they are working. Then we need to also work upon the stability and environmental degradation. We can, since stability is something that needs to be addressed, then we can come up with various encapsulation methods also, so that we can protect our device from any external triggers. If not others, at least from moisture we can protect our material. And then again, these companies are working on it. Scalability, there are certain lines, pilot lines working in this area, but yes, that needs to be addressed. So there are so what we take away from this is that in order to have a perovskite solar cells at a grand level or at a commercial level, we need to have some policy making, we need to have a continued R&D, we need to have industrial collaboration, we need to have some fundings from the government in this area, in which all the issues can be addressed at a better level or at a world level. So as one of the things I have discussed earlier also, that we can go for deposition methods, like we can go for spin coat, we can go for one step deposition, we can go for vast vapor resistive reaction methods, and then we can also work on film quality, how we are able to get the film quality, which further depends upon the spin rate, the temperature, the viscosity, all those things. So there are different methods during the deposition that actually determine the cost, and it also determines the quality of the material or the quality of a device. So all those things needs to be addressed while keeping the cost low. So our main aim is to improve the power conversion efficiency and to increase the scalability, but by keeping the cost low. So all those factors that I have discussed, that needs to be incorporated for commercialization of these particular methods. Okay, so this is something that has been there, and you might have seen some papers related to this. So as I've said, that we have accumulated a lot of research data based on this perovskites, because if you can change A, B, and X, we can have different stoichiometric coefficient also, starting from 0 to 1. So we can have a lot of perovskite absorber materials for, like for different and we can obtain different band gaps for that. So can we make use of those studies, or we can have, as I've said, that we need to find a balance. We need to come up with deposition method, that for this particular combination, which deposition method is better. Even if deposition method is sorted, our material is sorted, then we also need to come up that how these materials are actually integrating to form are getting integrated, and which type of materials are required to form the whole transport layer and electron transport layers. So that also needs to be taken care of, all those things. That, and if I say with the help of machines only it is possible. If I say as humans, because there's a lot of data present online, so it's very difficult to come up with one solution. So we make use of one of the technologies, that is machine learning approach. So what it does is it basically accelerate our research. It helps us in determining the material properties, the device performance, and based on what data we are feeding into it, so that it can do. And it identifies some new stable perovskites for improved efficiency. We can also come up with new materials also. Let's say we can fix that I want this band gap corresponding to this deposition technology, what should be the possible combinations with the possible stoichiometric coefficient. So that also can be obtained with the help of a machine learning technique. Device optimization can also be done, because if I say I'm going only for the experimental, how many experiments as a human I can do in my lifetime? So that's not possible. So if I can have a guide that can tell me that, okay, these experiments has already been done, so instead of replicating it, you can extend your study based on this history, and then you can project towards the other materials. So that is optimization is also possible. It can also help in degradation analysis. Tell me that it can tell me the performance losses. It can also tell some corrective, say, actions that has been taken earlier, and guide me throughout the journey. It can also tell me the sharp values, interpretability. So what happens is, let's say I have fed all the data for a particular material system, and I want to analyze that material, and I want to see what type of analysis that material is giving me. So for that I can go for different type of algorithms. I can go for multiple algorithms, and I can also go for sharp analysis, which will tell me that in this particular method, this particular material, or this particular deposition condition, because deposition conditions are also many. We can have a different times, we can have a different temperature, we can have different pressure for different deposition methods. So it can tell me, okay, this is something that is determining the performance, I need to focus on it. So that is something very much possible. Another is cost and time efficient. Again, because instead of going for hit and trial methods and trial and error experiments, we can have a proper pathway, and we can have a proper guide towards the next material composition. And it can also helps in scalability from fabrication to commercialization, because the time is reduced. We can have a better performance analysis, we can have proper device optimization. So with the use of initial studies, we can make use of the new study. So generally we take 80, we use make use of 80-20 rule. From first of all, we create a data set. A lot of data set is present in online also, it is present. And then if you have some other parameters on which you want to work upon, then you can just gather those research papers and create a data set for yourself, and then you can start analyzing it. So generally we use 80-20 rule for the training and the test data. You can also go for 70-30, depending upon what is your requirement, what efficiency you are looking for. So that is very much possible. So there are different steps involved in it. We have data collection, we have feature engineering, then we go for first of all we collect the data, then we see its feature engineering to see what features are we looking for. Then we have to select the model selection that corresponding to our features, what are the models present and how my models are behaving. And based on those models, I can just make some evaluations. I can study that, okay, this is the interpretation out of it, so that can be used. This whole thing actually takes a fraction of seconds, not much, I would say a minute. But this other processes, the data collection, that is something that takes time. So we have to be very particular what data are we looking into. So that is certainly time taking. So these are just few examples from the review articles that has been taken to understand. So if I say the first figure, it basically tells the impact of the temperature, the exposure time, on my power conversion efficiency. So first graph is corresponding to the temperature on the power conversion efficiency. So this was for particular one set of materials. Methyl ammonium tin iodide was one of the material. So here one of the material was taken, and it was studied that this particular set at corresponding to different temperatures and humidity, how it is behaving. Secondly, it was taken care of for different exposure time. Then it was taken by combining temperature on RH by varying the power conversion efficiency. And the third is RH on power conversion efficiency. By RH, I mean relative humidity. So we can combine 2 to 3 environmental factors one at a time, or we can consider one at a time, and then we can interpret something out of it, that how my material system is behaving in this regard. Second plot that we can see here is it's basically a 4D plot. It is used to predict the band gap of a perovskite material with the different cations and halide ratios. So here if we can see, this is just a 4D plot. So here we can see that if we have the concept, if I want to see the contribution of one cation at a time corresponding to the other cations, how my band gap is increasing and decreasing. So here we have Cl divided by Cl plus Br, then we have bromine by bromine plus iodine ratio, and then we have chlorine depending upon chlorine plus iodine ratio. So this is actually the trend for band gap, increase or decrease of the band gap based on its cations or halides. And second is based on this methyl ammonium and formamidinium and cesium. So how my cations are behaving and how my anions are behaving, and what are their combinations. If we have different combinations of methyl ammonium and cesium and formamidinium, how that is going to impact my band gap. So just we can obtain this graphs by using our models. Another is our decision tree. So that is also very much one of the studies that can be done with the help of our data. So what the thing is that first of all we can fix one parameter. Let's say for this case we can fix one power conversion efficiency, that this is my main target that I want to achieve. Then I can have different branches corresponding to the tag. I just need to feed my data into it, and then I can come up with this decision tree by its own, in which my system will tell me that for this particular set of material composition, what is the impact of, let's say, temperature, what is the impact of pressure, what is the time, what is the contribution of electron transport layer. If I'm using this particular transport layer, then what is the impact of on efficiency that can be quoted. And then multiple factors, so whatever factors that we have created in our data set, that can be just seen in one group. So it's just like a hierarchy, and we can also change it. If my power conversion efficiency is my goal, or if my open circuit voltage is my goal, or whatever parameter I want to fix for the time being, I can, or maybe sometimes I want to see the phase. If you have data enough for that, that can also be quoted into that. So anything we want to visualize, and then we can also do a sharp analysis based on this to understand one, or we can increase or decrease the tree size. That like one to after 1 2 to 3 levels, generally we don't go more than that. So that is very much possible to understand what is going on behind. Because if I say, if I have, let's say if I have 1,000 data sets, or if I have 10,000 data sets, it's very difficult to see that what is the interrelation between all the parameters. So here I can get an idea that how many particular transport layer, let's say if I say titanium oxide, how many papers are corresponding to titanium oxide, corresponding to that particular environmental stressor, and corresponding to that and it is able to retain how much power conversion efficiency. So all those things we can just fit in our Excel sheet, or whatever data set we have, and then we can view the results. This is one of the work that I did, in which the band gap reduction was done based on this different composition. So one of the composition was done using lead based, and this was cesium. So the basis of this study was, as I've said, that if I can change cesium, formamidinium, and methyl ammonium, and I can change its stoichiometric coefficient also, so the range, so the total should have like a combination value is 1, but I can have A and B ranging from 0 to 1. Any value can be there. Similarly, lead was fixed, but halide, bromine, and iodide, for that also the stoichiometric coefficients were not fixed. So we got this data set from research papers, and the 80-20 rule was used for training and testing the data, and quite good efficiency was obtained from this particular analysis. So this study was done to determine the band gap in terms of ratio of chlorine, bromine, and iodine, the ratio that I have discussed earlier. So similar ratios was checked here. Then we checked the impact of one halide at a time by fixing the other, and then we see the impact of band gap on it. Similarly, the impact of cations also was checked because one of the cation is already fixed. So we checked the A cation here. So we varied the value of Fa, Ma, Cs, and then the combinations also we just checked it, and then we saw what is the value of the band gap based on this. Secondly, we also worked on the tin based, when we there was only rest of the things were same, but only tin based materials were there. And for this particular combination, the data set was not that much, but then we were able to get few data points out of it and then do some predictions based on it. So the first again corresponds to the prediction band gap for the perovskite based on their halides, and the second corresponds to the prediction of band gaps based on their cations. And third was the lead and tin. So as I have discussed with you that the lead increases the toxicity, but it supports our stability, and tin does the other way around. But can we do something related to this, that we can mix lead and tin? So here if you see in this combination, the cation and the halide was the same, but here again we varied tin and lead also. So few combinations of lead and tin were was also included, in which we can increase maybe the value of tin coefficient, and then we can just use a minimum value of lead, and then we can see what is the impact on its band gap, because it's not the band gap that will ultimately depend determine the efficiency of my material. I need to look on the stability. If I'm looking in terms of the commercial purposes, there are many other factors that needs to be considered. So I'll go for this. So here we see that when we were checking this tin based material, so the contribution by the chlorine was very less, so it was mostly from the bromine and iodine. So we were able to make few predictions based on halide ratios, and for cations also we were able to make few predictions, so we got some good results. And again, if I say in terms of multi-junction technology, then again the same material compositions can also be used to increase the efficiency of our material. And we can also go for individual material composition that I have said. But again, if I say that if I use multi-junction technology, then it can increase the actually it can surpass the limit of only 30%, and we can go beyond this. So that is something very important. And if we integrate perovskite with silicon or any organic subcells, then we are able to obtain any next generation photovoltaics that will help in performance, in better performance, and it will also help us in commercial level scaling for industrial purposes. So that is very much important. So the same study that I have discussed earlier, that can be extended to multi-junction technologies also. We can go for different compositions of perovskites, different deposition methods, different ABX3 compounds, and then compositions, and then integrated with silicon. That can be done, or maybe perovskite combination, depending on what is our requirement. That can be obtained. That's very much possible. So, what is the contribution for the policy, regulation, and funding drive for perovskite solar cells? So, first is that there is a boost in the demand, and then for that we need to go for we need to accelerate our research. So that is one thing. Another is that the government also has to play a vital role. So as initially, if I say a decade back, the rules were quite strict, but now as we see, especially in China and in other countries, European countries, it is seen that the governments are supporting this research. The governments are helping in studies of this researches, and they are also helping in decreasing the installation cost, and they are providing certain benefits to the consumer. So that is something a government can do, and they can contribute so that this research can go on and move forward.
मगजमारी कर रहा है तुम लोग किधर लगा बोल अभी
Hello. Hello? Oh, hello. Am I audible?
Yes, madam. Yes.
Oh, somebody
Yes,
just
ma'am. Yes,
screamed.
ma'am.
I just got
Yes.
scared.
Yes.
Yes, ma'am. You continue. It's a by
Okay,
mistake. Someone is the mic on.
okay. So, environmental regulations are also something that needs to be taken care of, because again, the carbon footprints are there. So that is something we need to take care of when we talk about technology, when we talk about moving towards the next solar technologies. But then again, we have to keep something in our mind, being as humans, that it should always help us, but it should also be sustainable. So that is something we have to shift our focus towards. Industrial partnership and collaborations are also important for commercialization. And then again, international collaborations. It's not just that we as researcher working in one country are contributing to our country only. We can maybe go to some other country, gain some exposure from them, give our knowledge to them, and take their knowledge back to our country. So these type of international collaborations, and some of you might be working on some international collaborations and going for other researches. So this is something that is always important and vital also for any country's growth, or I would say at a world level. For promoting any technology, because if it's not that this one country is going into a certain technology revolution, the other is not. We have to go together and certain frameworks has to be made, certain standards has to be made when we are talking about, because something new is coming up. So certain standards are required, certain material compositions are required. So if we are able to attain all those things, we are at the safer side, and we can obviously progress from silicon to perovskite and maybe to multi-junction solar cells in the coming years, by able to harness maximum solar energy from the sunlight. So this is all about my presentation. Thank you very much. Yeah. So yeah,
Thank you, ma'am.
thank you.
On behalf of management, principal, and Atal FDP organization team, AC Patil
Yes,
College of
sir.
Engineering,
Sir.
I
Sir.
express my deepest yes, sir.
If there are any questions from participants, please take those questions.
Yes, please.
Okay, sorry.
I'll just take a minute. Yeah, one more thing, that I'm actually working in this area, and I also have some experience in the scabs also. And this whatever areas I have discussed with you, I am exploring these areas. And if anybody wants to collaborate, or anybody wants to need any help for this, any student is there or any faculty is there, so I can have a discussion with them. So during my PhD, I would like to mention that scabs is something I started recently, since 2 years back. I have worked on some codes related to Silvaco and Centaurus. TCAD is something that I used during my PhD. So if there is any help regarding that, how to take the materials, how to do the electro-optical simulations, if there is any help regarding that, and how this machine learning algorithms, what are the new applications of that, if what new projects I'm working on, if anybody is interested, they can just get back to me. So maybe the organizers can share my email ID with you, so you can always get back to me. That's not a problem. I'll be happy.
Okay, madam. Sure.
Yes, ma'am. Sure. Sure.
Participants, if you are having any question, please ask.
Oh, some are asking my email ID, so I can share my email ID with you.
Yes, ma'am. We'll update on Atal FDP WhatsApp group also.
Yeah.
Please
Okay,
share
okay,
us
sir.
to your.
Okay, sir.
Sir, we'll update your mail ID on WhatsApp group also.
Sure. Fine.
Hello, madam. One question from me.
Yes, sir.
If anybody wants to manufacture or fabricate this perovskite solar cell, is there an easy way?
Sir, by manufacturing, I would say that we are not at a manufacturing state, but yes, fabrication can be done. The thing is that we can just do the simple analysis by using a spin coater, but in order to have the the metal contacts, for that we need to have some lab setup. Another thing is just as precursors and the spin coater or maybe a slot dyeing technique that can be used for that. But then they can refer to certain papers, because manufactured depositing any layer of perovskite on a glass substrate is not a problem, but what happens is it degrades. So to prevent its degradation, we make use of glove box that is actually having an inert environment inside. So it is we are not getting exposed to any external environmental factors. So initial studies, yes, it can be done, but depending upon what material combination we are using. If I say just only the methyl ammonium lead iodide, there is a very high possibility that it will degrade. Yes, if we can just manufacture it, and within that time, if we can uh, get that electrodes done then and there only, and then we can measure its IV characteristics through Keithley. For that much amount of time, it should sustain. But again, what is your efficiency you are targeting for? That is something needs to be taken care of.
Okay, madam. Thank you. Your talk was very nice.
Thank you so much.
Madam, another question. You talk regarding multi-junction of perovskite and silicon.
Right.
Till date, is it commercialized?
No, sir. Even perovskite, any form of perovskite is not yet commercialized. One, I would say, just a pilot project, as I have mentioned, that is going on at Oxford PV, but commercialization is not yet possible. 95% industry is ruled by silicon. Because of its stability is a problem right now. That's why I have said that a lot of work is being done, because it has the potential, but it has not reached to a level that we can commercially use it. So that is something needs to be addressed.
Okay, thank you. Thank
Thank you,
you.
sir. Okay. Thank you, everyone.
Ma'am, one question from the participant in the chat box.
Yeah.
I will read it. If I consider a new material and I am the first user, how
Hmm.
can I obtain the material property for the SCAPS 1D?
Yeah, what you can do is there are certain materials. So if they have worked on scabs, if they have installed the scabs, in the scabs itself, there are certain materials already given. So there is a text files in the material given in that. So what they can do is that they can create a copy of that file, and in that file, what they can do is when they are entering the material properties. So I will tell you the shortcut. Just open the scabs material. In that you specify your layers: layer 1, layer 2, layer 3. Then go to one particular layer, and in that layer only there are certain material properties: band gap, the like accepted density, the donor density, all those materials, the mobility, and one more thing, there have to be their absorption coefficients, that also needs to be included. So they can enter those values manually, and then they can save those files in the scabs folder itself. So yes, it can be done. I hope I have answered your query.
Yes, ma'am.
Yeah.
Is any question from the participants? Okay, ma'am. Thank you. On behalf of
Thank you
management,
very much.
principal, and Atal FDP organization team, AC Patil College of Engineering, I express my deepest gratitude toward the Dr. Shika ma'am. Her talk is very greatly beneficially researchers and
Hello,
professionals. Those are working on computational
am I audible?
work in photovoltaic area. Thank you, ma'am. Yes,
Thank
sir.
you, sir.
Amol, sir. Yes. Amol, sir, please stop the recording. Amol, sir, is it audible, my voice?
Okay. Can we leave, sir?
Yeah, ma'am. Yeah. Thank
Okay.
you.
Thank you so much, sir. Thank you for the invitation.
Thank you,
Yeah.
ma'am, for the
Okay.
Thank
session.
you, ma'am.
Thank you. Thank you so much.